4 million tons of pesticides are applied to agricultural land every year, creating a chemical pressure that has severely degraded the soil. Thousands of ducks are released directly into the rice paddies in the middle of the growing season with no fences or constant human supervision. Why would such a chaotic release of animals not lead to the total destruction of the fragile crops? At first glance, the sight of thousands of birds moving through the fields suggests a disaster for the sensitive ecosystem. One might assume the rice would be trampled or eaten before the harvest, but in reality, the ducks ignore the grain and focus on the pests and weeds that threaten the yield. This biological intervention serves a critical purpose. China has chosen this specific method to rescue more than 40% of its farmland from the long-term effects of heavy chemical saturation. One can notice how the ducks navigate the narrow spaces between the stalks as the equipment of nature replaces the sprayers of industry. It gets more complex further on. After just one growing season, the rice fields did not collapse under the weight of the biological presence. Instead, the soil and the water began to show signs of recovery that exceeded the expectations of modern agronomists. Everything only gets more complicated when considering the sheer scale of the environmental damage previously recorded. The method challenges the dominance of modern industrial agriculture by utilizing a symbiotic relationship that has existed for centuries. It is visible how the movement of the birds oxygenates the water, while their waste provides a natural fertilizer that the degraded earth can finally absorb. The process is only gaining momentum. The ancient practice proves that industrial quantities of chemicals are not the only solution for large-scale food production. A method that appeared superficially simple and even disorganized has managed to stabilize the ecosystem beneath the surface of the water. This shift from synthetic additives to natural cycles marks a significant transition in the management of vast agricultural territories. The transition to biological pest control represents a fundamental change in how the landscape is managed. The rice continues to grow toward the harvest, while the soil quality improves with every passing week. Thus, the farmland reaches a state of balance that allows the production cycle to continue without further chemical intervention. 100 years, less than a single century, is the duration in which global agricultural land has undergone a total transition to mechanical operation. Why has the landscape of farming shifted so radically from manual effort to industrial power? It would seem that the traditional methods of the past were sufficient for generations, but the demand for rapid output dictated a different path. This mechanical evolution replaced human labor with specialized machinery like transplanters, harvesters, and high-capacity sprayers, while the introduction of synthetic fertilizers accelerated the natural growth cycles of crops to unprecedented speeds. The transition to the next level of production involved the systematic application of pesticides. These chemicals allowed for the suppression of diseases and pests at a scale that had never been witnessed in the history of cultivation. As a direct consequence, the total volume of food produced globally surged many times over. Yet this industrial triumph carries a physical toll that is becoming impossible to ignore. One can notice how the environmental balance shifts, as agriculture now accounts for approximately 20 to 25% of all greenhouse gas emissions worldwide. Chemical fertilizers and the physical degradation of the soil constitute the primary sources of these atmospheric emissions. Pesticides alone have significantly depleted the populations of soil microorganisms, effectively halting the biological cycles that once functioned to maintain the fertility of the earth without human intervention. But this is just the beginning of the crisis. It only looks obvious that adding more chemicals would solve the problem of declining output. But in reality, this creates a state of dependency. Research indicates that more than 40% of the world's agricultural territory is currently losing its inherent capacity for natural regeneration. Farmers are now forced to apply increasingly larger volumes of chemical agents and fertilizers simply to prevent their yields from falling below previous levels. The situation reaches a critical threshold when considering that over half of the global population relies on rice as their primary source of nutrition. Rice fields function as more than just a method of farming. They serve as the central foundation for the security of the global food supply chain. It is visible how the weakening of this specific ecosystem allows risks to migrate beyond the borders of individual fields, eventually threatening the entire network that sustains billions of people. a dangerous and quiet cycle begins to manifest, eroding the resilience of agricultural systems with every passing season. At first glance, the modern industrial approach seems like the pinnacle of efficiency, but in reality, the system is generating its own internal failures. The equipment continues to move across the fields, but the underlying biological structure is fading. Everything only gets more complicated as the demand for food continues to rise against a backdrop of diminishing soil health. If the current trajectory of modern farming is actively producing these structural problems, the question remains where the physical and technical solution to this imbalance truly lies. 600 years is the remarkable duration over which a specific biological model has sustained agricultural stability without the intervention of synthetic chemistry. Why did ancient rice-growing regions in East Asia avoid the soil exhaustion that plagues modern industrial farming? It only looks obvious that a field should serve as a single-purpose production surface, but in reality, these areas functioned as complex, self-regulating ecosystems where rice and ducks coexisted in a symbiotic loop. The effectiveness of this ancient method stems from biological balance rather than sheer mechanical output, proving that sustainable yields were possible long before the advent of modern pesticides. Ducks are released into the flooded paddies shortly after the manual transplanting of seedlings is completed. One can notice how the birds move continuously through the shallow water throughout the daylight hours, their webbed feet gently stirring the top layer of saturated mud. This physical agitation oxygenates the water and prevents the consolidation of the soil surface. The ducks systematically consume young weeds and various insects that would otherwise threaten the integrity of the grain stalks. But this is just the beginning. The process is only gaining momentum as the ducks provide a continuous supply of organic nutrients. Their droppings fall directly into the water, where they are integrated into the soil as a natural replacement for external fertilizers. The equipment of nature replaces the need for heavy machinery or chemical inputs. It is visible how the animals navigate between the rows of rice without damaging the crop, acting as a mobile filtration and fertilization system. Agricultural records from across the centuries confirm that this model maintains stable yields over vast periods of time. The system ensures that the soil is not exhausted by the demands of the harvest, as the nutrients are recycled within the same space. Everything only gets more complicated when modern methods attempt to replicate this balance with artificial additives. In this traditional environment, pest outbreaks remain rare because the natural predators are already present on the surface of the water. This historical practice demonstrates that the solution to modern agricultural crises may lie in the integration of livestock and crops. The rice duck model illustrates a cycle where waste becomes a resource and labor is performed by the ecosystem itself. The soil remains fertile and the water clean, allowing the fields to sustain themselves season after season without interruption. From here, the transition to sustainable production moves forward by looking toward these refined ancient structures. 100% of the young rice plants appear vulnerable when the first flocks of ducks are released into the flooded fields. Why do farmers risk the integrity of such a fragile crop by introducing dozens of active animals? At first glance, the heavy impact of webbed feet seems capable of crushing the entire harvest before it can even mature. But in reality, a precise biological synergy begins to unfold within the ecosystem. The ducks demonstrate a specific behavioral pattern by largely avoiding the tender green rice shoots altogether. Instead, they direct their attention toward everything that moves beneath the water's surface or grows at a faster rate than the primary crop. The process is only gaining momentum as the birds focus on the exact elements that human farmers struggle to manage manually. Brown plant hoppers, stem borers, and leaf hoppers are systematically hunted as a primary food source for the flock. As the group moves ceaselessly through the aquatic rows, they interrupt the pest life cycle at its most critical early stages. One can notice how the population of harmful insects drops significantly within a period of just 3 weeks. This constant movement simultaneously agitates the surface of the water, which effectively destroys mosquito larvae and other parasitic organisms. It gets more complex further on. Because of this natural predation, the necessity for chemical pesticide spraying is reduced to almost zero in many cases. Weeds also lose their ability to dominate the landscape as they did previously. Ducks consume young weed shoots, duckweed, and wild rice, which are the very plants that typically compete with the crop for essential nutrients. Every single step the birds take prevents weed roots from establishing a firm hold in the mud. This ensures that dense mats of unwanted vegetation cannot form around the base of the rice stalks. The equipment of nature operates here with continuous efficiency. It is visible how the water is stirred into a murky consistency, which introduces vital oxygen into the liquid and the uppermost layer of the soil. This mechanical disturbance prevents the soil from compacting and limits anaerobic conditions. Because the earth remains loose and oxygenated, the rice roots are able to penetrate to a much greater depth and gain structural strength. Many researchers observe this phenomenon as a form of natural tilling that occurs 24 hours a day without the use of heavy machinery. Throughout this entire cycle, duck droppings are distributed with perfect uniformity across the field. One can notice how this creates a continuous stream of organic fertilizer, rich in nitrogen and vital organic matter. This nutrient source provides a steady supply of energy to both the soil and the plants. The process is far more controlled than the over-application often seen with chemical alternatives. This steady infusion of nutrients minimizes the risk of polluting surface and groundwater through excessive runoff. Every movement of the flock contributes to a closed-loop system of growth and protection. Thus, the biological interaction reaches a state of equilibrium where the plants and the animals thrive in a shared environment. From here, the rice continues its development into a robust and healthy harvest. 150 to 300 ducks per hectare is the calculated density required to transform a chaotic flock into a precision biological tool. Why must farmers regulate the introduction of these birds with such strict timing? A mistake of only a few days can jeopardize the entire harvest. If the ducks enter the paddies too early, the fragile young seedlings will be crushed under their weight. But waiting too long allows weeds to gain a foothold that the birds can no longer suppress. The rice plants must grow for exactly 2 to 3 weeks after the initial transplanting process before the first duckling is released into the water. During this window, the stalks gain enough structural integrity to withstand the constant physical movement and the swirling of the water. One can notice how the ducks navigate between the rows, their webbed feet disturbing the soil surface without snapping the hardened stems. But this is just the beginning. The density of the birds is a parameter derived from extensive agricultural studies conducted in Japan and China. While 150 ducks might suffice for certain soil conditions, other rice varieties require up to 300 individuals per hectare to maintain the necessary pressure on pest populations. If the concentration of ducks falls below these specific numbers, the biological impact remains too weak to eliminate the need for synthetic chemical inputs. It gets more complex further on. At first glance, more ducks might seem more effective, but in reality, exceeding the 300 bird limit creates a destructive environment. One can notice the water becoming excessively clouded with silt as the birds forage too aggressively. This thick suspension of mud blocks sunlight, which directly stresses the root systems and inhibits the ability of the rice plants to perform photosynthesis. Everything only gets more complicated when the rice reaches the stage of panicle initiation. This is the moment when the plant begins the internal preparation for flowering, and it marks the absolute deadline for the removal of the ducks. The equipment of nature must be completely withdrawn from the field at this precise junction to prevent even the slightest disturbance to the maturing stalks. Because the rice is now entering its most sensitive physiological phase, any physical contact can reduce the final grain count. One can notice the farmers clearing the paddies entirely, ensuring that the development of the panicles proceeds in total isolation from the flock. Therefore, the removal is executed with the same level of technical precision as the initial release. The birds are guided away from the water, and the rice plants are left to transition into the final stage of grain formation in a stable environment. 50 to 70%. This is the scale of the reduction in pesticide expenditures recorded in rice duck farming systems across China and Japan. Why do these costs plummet so drastically when the ducks are introduced? It only looks obvious that the birds eat pests, but in reality, their presence creates a biological barrier that replaces expensive chemical treatments. Chemical fertilizer costs also see a significant decline of 20 to 40% as the ecosystem begins to sustain itself. Total input costs per hectare are reduced considerably, frequently starting from the very first growing season. Small farming households rely on this efficiency for survival, while global prices for agricultural inputs continue to climb. But this is just the beginning. One can notice how the economic value of the grain itself undergoes a transformation. Rice harvested from these integrated systems is officially classified as ecological or low-chemical grain. In numerous Asian markets, this premium product commands prices 10 to 30% higher than conventionally grown alternatives. Consumers demonstrate a clear willingness to pay more for safety and sustainability they can verify. The duck flock develops into a secondary economic asset of significant value alongside the grain. With constant access to natural food sources within the flooded fields, the birds grow at a rapid pace. This natural diet ensures a low reliance on commercial feed and minimizes the need for antibiotics. The equipment of the ecosystem, driven by the movement of the birds, allows farmers to sell meat and eggs at the end of the season. This creates an additional income stream that remains entirely independent of fluctuating rice prices. The process is only gaining momentum as it spreads market risk across two distinct commodities. In many observed systems, the revenue generated from the ducks is sufficient to offset a major portion of the rice production costs. One can notice how an ecological cycle stabilizes into an economic model capable of balancing its own finances. The transformation moves the farm toward a state of heightened fiscal resilience. The financial pressure on the producer eases as the system matures. Thus, the integrated model reaches a standard where ecological health and economic profitability work in unison. 20 to 30% less methane is released into the atmosphere from these rice fields compared to conventional chemical-intensive farming plots. Why does the withdrawal of synthetic substances trigger such a drastic shift in the environment? It only looks obvious that removing toxins would help, but in reality, the change begins with the physical properties of the water itself. The liquid gradually becomes clearer, algae levels drop significantly, and the pungent smell of anaerobic decay vanishes. This transformation marks the end of the field operating like a starch factory. Creatures that were once pushed out of the farming system begin to return. Beneficial insects are the first to appear in the clearing landscape. They are followed closely by frogs, small fish, and dragonflies, while water birds settle in the maturing rice stalks. One can notice how the rice field slowly reclaims its role as a living ecosystem. The process is only gaining momentum. The constant movement of the ducks disrupts anaerobic conditions within the soil. This disruption targets the primary factor behind methane production in flooded rice paddies. It is visible how the birds navigate the water, their webbed feet stirring the sediment and introducing oxygen. Because of this mechanical action, the fields do not just reduce their environmental impact, but actively contribute to mitigating climate change on a global scale. At first glance, the rice duck model is simply less harmful agriculture. But in reality, it represents a move toward regenerative farming. One can notice how the soil is restored over time. Biological cycles are reconnected as the ecosystem begins to sustain itself over multiple growing seasons. The system no longer requires rescue by chemical inputs, as the natural balance maintains the health of the crop. Dust and silt settle in a new, stable pattern beneath the canopy of green plants. It gets more complex further on. The field functions as a self-regulating unit where every organism plays a technical role in production. From here, the transformation moves to the next phase of processing as the soil structure strengthens. The material cycle concludes this phase, opening the road to a permanent state of ecological stability. Thus ends one of the key stages of transitioning toward a fully sustainable agricultural model. 450 kilograms of pressure per square centimeter represents the structural resilience required for such complex agricultural integration. Why is the integration of waterfowl into cereal crops considered a high-precision engineering task? At first glance, the method appears to be a simple return to nature, but in reality, the biological variables require the same level of calibration as a chemical reactor. The exact timing of the avian release, the calculated density of the flock per hectare, and the microscopic management of water levels determine whether the system thrives or collapses. But this is just the beginning. The camera glides along the perimeter, where a single oversight in monitoring rice elongation can transform a beneficial symbiotic relationship into a catastrophic production risk. One can notice how the equipment remains secondary to the biological clock of the animals and plants involved. Automated systems and human supervisors must account for the relentless pressure of local predators. Snakes, foxes, feral dogs, and various birds of prey pose a constant threat of significant biomass loss if the containment and protection protocols are not executed with absolute rigidity. It gets more complex further on. Labor shortages in specific geographic regions often create a critical barrier to the adoption of this model. The system demands constant human presence or advanced surveillance to mitigate the risks inherent in open-field biological management. Without sufficient supervisory capacity, the potential for failure outweighs the organic benefits. Every ecosystem possesses a unique chemical and topographical signature that may or may not support such a delicate balance. Areas lacking a consistent and stable water supply cannot maintain the hydraulic requirements of the rice paddies or the physiological needs of the ducks. The process is only gaining momentum as terrain analysis becomes the deciding factor. Steep gradients or uneven topography prevent the uniform distribution of water and nutrients, rendering the system mechanically impossible. Furthermore, rice paddies that have suffered from heavy industrial pollution or chemical saturation fail to provide the necessary biological foundation for the organisms to survive. One can notice how the soil quality dictates the limits of the entire operation. Therefore, the rice duck model functions not as a universal industrial template, but as a specialized technological solution. It requires a specific set of environmental parameters, careful adaptation to local variables, and application under strictly controlled conditions. Everything only gets more complicated as the transition to the final evaluation begins. The complex interplay between the environment and the livestock finds its equilibrium within these specific boundaries. This phase of the agricultural cycle reaches a point of stability, preparing the land for the next stage of the seasonal harvest. 90 meters deep, that is the staggering distance the roots of a willow tree must penetrate to reach the subterranean water tables hidden beneath the scorched Kubuki Desert. When the initiative to utilize rabbits as an instrument for ecological restoration first emerged, the primary objective was clear. Why did the survival of the fauna depend entirely on a single botanical species? The answer lies in the extreme hostility of the environment, where only the willow possessed the physical resilience to endure shifting dunes and relentless thermal stress. This plant functioned as the mechanical foundation for the entire project, anchoring the loose terrain and slowing the velocity of the surface winds. But this is just the beginning. It only looks obvious to plant a tree, but in reality, the surface of the sand reaches 70 degrees Celsius, a temperature capable of incinerating organic matter in minutes. The atmosphere in this region is thick with wind-blown sand that acts like abrasive razor blades against any exposed bark. To ensure survival, specialized teams must identify microscopic pockets of moisture buried deep within the dunes. One can notice how workers immediately reinforce every planting site with wire mesh and reed barriers to prevent the desert from reclaiming the whole before the willow is even placed. The young saplings receive a coating of moisture-retaining polymers and are physically bolted to wooden frames to resist the nocturnal gales. Everything only gets more complicated as the irrigation process begins. Hydraulic systems deliver water with extreme precision, providing only the minimum volume required to stimulate the roots to push downward. It is visible how the plant is forced to seek its own survival by tunneling toward the deep moisture layers. Once these initial bands of willow trees reach sufficient density to cast shadows and trap humidity, the next phase of the restoration model was initiated. This involved the introduction of Rex rabbits into a strictly regulated and enclosed ecological system. These animals were never intended for the open wild, but were instead integrated into specialized farming structures where their presence served both a biological and industrial purpose. The process is only gaining momentum. At first glance, the Rex rabbit is merely a source of meat and fur, but in reality, it functions as a biological chemical plant. Their manure contains high concentrations of nitrogen, phosphorus, and potassium, which are the exact chemical elements the barren desert soil lacks. One can notice how the application of this organic waste causes the loose sand to bind into a cohesive, nutrient-rich layer of humus. This is not the limit of their contribution, as the rabbits possess a unique digestive limitation regarding grass seeds. Because the seeds pass through the rabbit system entirely intact, they are deposited across the landscape inside a natural casing of fertilizer. It gets more complex further on. This biological mechanism allows vegetation to sprout autonomously, even in the most brutal thermal conditions. the ecosystem gradually transitioned into a self-balancing machine where the willow canopies provided the shade and nutrition the rabbits required. In a reciprocal cycle, the rabbits generated the humus that stabilized the soil and prevented further erosion. This closed loop transformed every hectare of the former wasteland into a factory capable of producing over 5 tons of organic fertilizer annually. Within a period of 3 to 5 years, a stretch of rock-hard ground is converted into fertile agricultural land. Transition to the next level. 200 million willow trees now form a massive green barrier that has fundamentally altered the local climate. These botanical walls have successfully reduced wind speeds by 90% and locked 15 million tons of sand in place annually. One can notice the physical change in the landscape across 800 square miles, where greenery has replaced the shifting dunes. The population of 1,200,000 Rex rabbits now sustains an economy generating over 100 million yuan every single year. This provides thousands of local families with a stable income in a territory that was once classified as completely uninhabitable. Thus, the desert ecosystem reaches a state of stability, allowing the production cycle to continue its expansion. 1,000 years of ecological interaction prove that the integration of rice and ducks is far more than a simple agricultural technique. Why does this ancient methodology resurface in an era of industrial dominance? It only looks obvious to rely on chemical additives, but in reality, the biological synergy between these species creates a self-sustaining cycle that modern synthetic systems often fail to replicate. The process is only gaining momentum as global farming begins to confront its own physical and chemical limitations. At first glance, the strategy appears to be a step backward into the past. In reality, the way forward is dictated by a deeper technical understanding of natural mechanisms rather than the pursuit of increasingly complex machinery. One can notice how the ducks move through the flooded paddies, their paddles disturbing the water at a constant rhythm to oxygenate the root systems. This is not the limit of their utility. Ecosystems that were previously ignored under the constant pressure to maximize yields are quietly demonstrating the superior efficiency of biological balance. The camera glides along the verdant rows, where the absence of synthetic pesticides is compensated for by the natural foraging of the birds. Everything only gets more complicated when we attempt to replace these natural services with industrial chemicals that eventually degrade the soil structure. The principles of global food security will likely be reconstructed upon these foundations that seem old, yet remain technically relevant in the 21st century. This transition to the next level of farming involves observing how nutrient cycles are closed without external waste. One can see the natural fertilization occurring as the ducks contribute nitrogen directly to the soil while consuming pests that would otherwise require heavy chemical intervention. The story of the rice paddy and the duck concludes as a testament to the power of systemic equilibrium over sheer mechanical force. This symbiotic relationship ensures that the land remains productive for future generations without the exhaustion common in monoculture systems. The journey toward a sustainable food supply continues through the refinement of these natural systems.